Hi everyone, so today we are going to learn about the distance from a point to a line. So I know you also have distance from a point to a plane in the same note. We're only going to do the part about a point to a line today, and the next video will be about a point to a plane. Okay, so first, before we even get started, let's recall the formula for distance between 2 points in R2. So we learned this back in grade 10, sorry about that. And basically, we did an alternative form of Pythagorean theorem to learn about this. So if you have a point x1, y1 and a point x2, y2, the distance between them can be seen as the hypotenuse of a right-angled triangle. Okay, where the distance of this is just the distance between the x values, and the length here is the distance between the y values. So therefore, this creates a hypotenuse, where the other two side lengths are x2 minus x1 quantity squared and y2, y1 minus y1 quantity squared. And then to isolate the distance, you take the square root of the whole thing. So that was back from grade 10. We're going to expand that slightly to determine the distance between a point and a line. Now, I will say I used to go into more detail about teaching the derivation of this formula. Today, I'm basically going to give you some basic concepts of how it's derived, but then give you what the formula is. So in this case, we know the equation of a line in its Cartesian form. This is R2, and we are given the coordinate of a point. Okay, so the point that we are given that's where the O's come in. So we want to know the distance between PO and this red line, which is indicated by this formula. So the distance that we want is going to be the shortest distance, which is when you create a line perpendicular to the line. Sorry, so you create a line segment perpendicular to the given line. So in this diagram, it's the magnitude of the vector POR. So I can make that a vector, where you notice it hits at a 90-degree angle. So this is actually a projection of POP, so P is any point on the line, onto POQ, okay? So basically, it's a projection of any vector to the normal. So the distance between the given point and the line is represented by this formula. Now, if you are curious about how this was derived, I would encourage you to check the textbook, or you can ask me where to look, because it is manageable for you to understand how this is derived. I just know that this is the end of the year, and usually learning something that you're not going to be tested on at this point is going to mostly fall on deaf ears. Okay, so this is the formula, the absolute value of AXO plus BYO plus C divided by the square root of A squared plus B squared. So A, B, and C are from the Cartesian equation, and XO and B and YO are the point in question. So let's apply this, okay? So determine the distance between 15, negative 9. So XO is 15, YO is negative 9, and this line. So notice that this line is in vector form, so we need to change it to Cartesian. Okay, so remember here that the slope of this line would be negative 1 over negative 2, so a half. So therefore, the slope of the perpendicular, sorry, that's positive a half. The slope of the perpendicular would be negative 2. Oh, sorry, I did that wrong. Y'all are like, Mrs. Weens. I apologize. Sorry, that's the direction vector. So the slope is negative 3 over 4. There we go. So the slope of the perpendicular is positive 4 over 3. So the normal vector is 3, 4. So we have 3x plus 4y plus c equals 0. And then you could put the point negative 2 and negative 1 in, and you'll find that c is equal to positive 10. Okay, so I'm assuming that you know how to solve for that from before. Okay, so now our A is equal to 3, and our B is equal to 4, and our C is equal to 10, and we put that all into this distance formula and just see what pops out. So distance is equal to the absolute value of 3 times 15 plus 4 times -9 plus 10 all over the square root of 3 squared plus 4 squared. Okay, so when you put that into your calculator, you get 3.80 units. So that's how far apart this point is from this line when you're looking at the shortest distance. Okay, calculate the distance between two parallel lines. Okay, so in this case, we have two parallel lines. So what we're going to do is find the point on one line. And then we're going to find the distance between that point and the other line using our given formula. So find a point on one line. So the y-intercept of equation 2, the second equation, is if you put in 0, you get -5. So we're going to find the distance between, so find distance between 0, -5, and equation 1. Okay, so distance is equal to A of the line, so 5, so sorry, the absolute value of 5 times our point, 0, x, plus our B value, -12, times the y of the point, so -5, plus C, 60, all over square root of A squared plus B squared. So square root of 5 squared plus -12 all squared. So when you put that into your calculator, you get 120 divided by 3 units. Okay, so both of those examples are in R2. We also need to look at R3, which is quite a bit different. Okay, so the distance from a point to a line in R3. So let's create this little diagram here. So we have our line, and here's its vector equation. We have that a point P, a given point, and this is the distance. PR is the distance from the point to the line. And then we can create a vector QR, which contains an angle theta with the line. Okay, so let's recall that just by SOHCAHTOA, sine theta in this case would be opposite. So D over hypotenuse, so the magnitude of vector QP. Now, if we rearrange this, we get D is equal to the magnitude of QP, so any point on the line to the given point, times sine theta. Okay, now if we take this further, we will remember that this cross product can be used. So basically what this boils down to is that the distance is equal to the magnitude of the cross product of the direction vector crossed with QP, where Q is the point on the line, okay, all over the magnitude of the direction vector. Again, you guys can do this, prove why this is true, okay, by looking at the textbook if you'd like, or just memorize the formula. It's kind of your choice at this point. So it's worth noting, though, that Q, let me get a different color. Q is a point on the line. So Q is a point on line with direction vector M. Okay, and P is the point in question, the known point. Okay, so let's just do one example where we're actually calculating this. So determine the distance between this point to this line. Notice that we're given the vector equation. Okay, so the first thing we want to do is determine what P and Q is. So we know P is the point. Q is the point on the line. So 1, 2, -1. So what we want to do is find QP. Okay, so that's OP minus OQ. Okay, and that in this case is -2, -1, and 7. Okay, you do all of the P minus the Q. So like -1 minus 1 is -2, etc., etc. So then you can find the cross product of QP crossed with M. So in that case, it'd be -2, -1, 7 crossed with the direction vector 0, 1, 1. Okay, and when you do that, you get 8, -2, 2. Okay, so then the distance is the magnitude of 8, -2, 2, divided by the magnitude of M. So 0, 1, 1. Okay, so this gives us root 72 divided by root 2, which is 6 units. So the distance between this point and this line in R3 is 6 units. Okay, so those are the formulas that you will need to find the distance between a point and a line in R2 and a point and a line in R3. Thanks for watching, guys. Hope you learned lots.